Hello, welcome everybody. Today we have a very special guest with us, James McNay. Today's webinar, this is a part two of a series of webinars on how to effectively use certified equipment in fire and gas systems. And today's discussion will be on flame detection. I am Ted Stewart. I'm the Program Development and Compliance Manager here at Exida. Got a little bit over 10 years of experience in safety and high availability automation systems. I deal with manufacturing and lean process improvement. The companies I used to work for are Lockheed Martin and Missiles and Fire Control. As a test engineer, I then went over to Harris Corporation, working for wireless product groups with some classified different products. And now I'm here at Exida. I've been here for over 5 years. Love my job. I help manage the OEM certification division. I'm the deputy quality manager and the director of the CFSP program. So I get to wear a lot of different hats. Every day is a new experience. And today's experience is I get to work with one of the experts in fire and gas, and that's Mr. James McNay. James, go ahead and introduce yourself, sir.
Yeah, sure. Thanks, Ted. I'm James McNay. I specialise in the design of fire and gas detection systems. I'm the operations manager here at Micropack Engineering. And at Micropack, in the consulting side, we specialise in fire and gas mapping. Now, today's webinar is obviously going to concentrate on flame detection mapping, but the gas detection mapping is quite a significant field as well, and the two are typically carried together. Before entering the oil and gas industry, I was based mainly in commercial fire engineering, focusing on the design of bespoke buildings, which require more complex fire modelling and designs than your typical standard office blocks, for example. That happens to be quite a well-established field with some fairly well-established performance-based design guidelines. So it was a bit of a surprise coming into oil and gas, where the guidance relating to fire and gas detection is somewhat, well, varied, to be honest. It's therefore been a bit of a challenge to myself and a bit of a challenge to Micropack to try and increase the knowledge base relating to some of the basic principles relating to fire and gas detection and fire and gas mapping. So hopefully today's webinar will help us move towards this.
Awesome. Hey, thank you so much, James. And it's a privilege to have you on today's call, or on today's webinar here. But I got two real quick slides. We always have newcomers to Exida, so we always, for these webinars, so basically who is Exida? We were founded in 1999 by some of the world's top reliability and safety experts. Basically, you see the map. We are a global company all over the world. Little red dots, I say, for our new offices are popping up. Our most recent one was India this year. We just finally have it finalized, but we do anything in functional safety, alarm management, cybersecurity, etc. We do get involved with the complete supply chain of functional safety in all the different industry sectors. For example, we're going to be doing a lot of fire and gas as we see that it becoming an increasing demand in the industry. But we'll deal with anything from the original equipment of those manufacturers who need the product certification through to the end users that will actually use these products. And that's why we get involved with that complete supply chain, or that complete life cycle supply chain, I guess I could call it, but anything with training, consulting, procedure related, functional safety, security, and reliability is what we focus in. And you'll see here there are 6 different areas that we help in, which is the consulting, the tools, the product certification, training, any kind of reference material, and of course for people, the professional certification. Today's webinar will be focusing kind of within the consulting and within the product certification, and sharing what the value is and why people are even getting things certified. And the consulting aspect is where we're going to be talking about the flame mapping. So today's agenda, and thanks everyone for being on today's webinar. You will notice a question tab there. If you have any questions throughout the presentation, by all means, ask those questions. If we don't answer them throughout the presentation, at the end, we'll open it for questions. We'll get those questions answered. And then after we do the second webinar today, we will send out a list of all the questions that were asked with the answers, and we'll provide the webinar itself as well. So thanks again, and I hope you enjoyed today's webinar. So my portion is on what is the value of product certification. And before we get and discuss that value, does everyone know what is included in a certification. Now, I'm not going to get into the very details, but I'll do it at a very, very top level. But basically, a certification is done by a third-party agency against a set of requirements, usually called a scheme, and it's based primarily on international standards. And for our sake today, it's either IEC 61508 for the manufacturer or IEC 61511 for the end user. Now, things can get certified like systems, products, components, personnel, functional safety certification. That involves a detailed analysis of both your engineering process and the design margins resulting in, let's say, a random failure rate for many different failure modes. And then what's becoming another increasing demand that we notice is in cybersecurity certification. That involves also a detailed analysis of the engineering process, but then again, now you have to look at the cyber defense mechanism and the network robustness. So what are the values in product certification? Well, the first three things I noticed is there's three main barriers that if you don't have a product certified, end users now have to worry about these things. And those things are the systematic capability rating, the architecture constraints for that, called the detector, and then now the failure rates for that PFD calculation of that product. And like I said, if this product is not certified, now all of a sudden this end user is going to have to figure out how to get the SIL rating for the SIF they're trying to develop. So let's talk about each one and what each one means. So the systematic capability rating. The first obstacle that gets cleared when you go through product certification is the systematic capability, which is basically established by attaining a quality management system audited per IEC 61508. So if the QMS, the quality management system, meets the requirements of 61508, a SIL capability rating can now be issued. And the higher the SIL rating achieved, the more effective that manufacturer's QMS system. So things that are asked in this stage are, well, how do you source or how do you find parts suppliers? How do you make modifications? How are returns and recalls handled? Things like that will be considered, they'll be evaluated, and based on your response and what you say and what you have written down, helps determine what SIL rating you can have on systematic capability. Now, when that detector becomes certified, that systematic capability of the device is now shown on the certificate. So you'll see that there. Without product certification, this barrier becomes very hard for end user to meet. They'll have to probably go through a proven in use type justification. And, that's going to take a lot of time. It's going to take a lot of money to get through it. And if a manufacturer can simply provide this type of certificate, that end user now has a huge selling point that they don't have to worry about meeting those requirements. Let's see here real quick. I do have a quick question, if I can get to it. Let's see here. Not clear. So we do have questions where this question here was when it goes through a certification process, you can get certified to different standards, whether it's IEC 61508 2000, 2010, and depending on their design and their capabilities, that manufacturer, when this was originally certified, they have that choice to pick. And now we are transitioning to where everyone should be up to the latest and greatest standard, but there are still products where you can still apply to 2000 based on the requirements from the field. When you go to the second obstacle that is cleared, that's your architecture constraints. This second obstacle is either done by the complexity of that device or by field operating history. So you can also call this Route 1H, you can call it Route 2H, or you can actually meet architecture constraints both ways, right? You can do 1H and 2H. Now, there's different SIL tables in 61508 and 61511, and you want to determine this architecture constraints depending on the SIL rating, right? So the end user, they'll use these tables when they want to develop and create their SIFs. So when you look on the certificate, you'll see that the end user now know how to calculate the architecture constraints using the 61511 table, right? So they can say, oh, HFT equals 0. I can go to this table. Okay, it's at cell 2. Oh, okay, this is what I need to do to develop my CIF. And so now you're giving them guidance on how to overcome this barrier. The third barrier. And so when you clear this third barrier, this is when the detector is certified for failure rates for that PFD calculation. If you're not too familiar with the PFD average calculation, it's basically an equation that's it's given in the standard. It has 9 different variables to achieve this PFD average, this probability of failure on demand, and it's based on the dangerous failure rates. It's based on systematic diagnostics, proof test coverages, test intervals, maintenance, and other conditions that are controlled basically by that product and how that end user is going to use this detector or this device. And from the product certificate, the end user now has the ability to take those failure rates of the device, and with the knowledge of these other variables that they control, such as how often they're going to be testing the CIF, they can now calculate that PFD average for the CIF. And every time I do talk about this subject, I always put that disclaimer in here that it's important to note that this PFD average is not a value that a device manufacturer should be providing. There are too many of the 9 variables from the equation that are going to have to be assumed if that manufacturer wants to provide such a number. So you need to make sure that this is left up with the end user. And if you do see a PFD average number, please do not use it unless you know what those variables are before you use it, right? And that's why one thing for us here at Exida is we used to give examples of how to calculate a PFD average in our reports. We removed it because people were using that as an actual for their product, and they didn't realize that it was just an example. So we've removed that to just eliminate that confusion. So now when you do have these products getting certified, certifying bodies now on the back, for us anyways, we publish these failure rate numbers with the different failure modes for the end user. They can now take these failure rates and apply them to their PFD average number. And if this is something that might be a little confusing, if you need some help, you'll have our contact information at this webinar. Send us an email. We have white papers on how to calculate this PFD average number, because we'd rather help you get through some of these hurdles, whether or not you're a customer of ours, just because I'd rather someone do something correctly than to move through thinking they've done something correctly, if that makes sense. And so what is the value to those manufacturers that are getting these products certified? Well, this third-party review of the product, our main objective is to find faults in the design resulting in a lower lifecycle cost, right? We want to find things before there's a redesign or they have to rework things. And obviously it helps increase the marketing and sales. Why? Because now end users can use something with the assurance that it's already gone through these 3 different obstacles. Sure, there's a cost associated to get something certified, but the goal is there's now a lower risk and an increased savings in the long term. And of course, with these reduced failures at the manufacturing site, there'll be less rework in the field. What about for an end user? What is the benefits of a product that's certified? Well, hey, you now have a product that's gone through the rigor. It has a better quality management system. It's going to have less spurious trips statistically. You'll have an increased safety. You'll have less field failures, a more robust system. And of course, now you have someone that's looked at this product that you are buying. We have a completely non-biased review of the product all the way down, because we do that FMEDA to it, all the way down to the nut and the bolt, looking at issues for possible problems. So we break down every product all the way down to its single components and then build it back up with assigning failure rates to each and every part. And so that's where the true value lies and why people are getting products certified. And now with that, I'd like to pass it over to James McNay, who's going to be speaking our second part of this presentation with flame mapping. And James, I will go ahead and make you the presenter.
All right, thank you, Ted. Okay, and hopefully I've got control now. We'll find out shortly.
That's great.
Thanks, Ted. We're going to be looking mainly at flame detection mapping, as Ted has discussed. Before we get into the actual mapping process, we're going to want to ask the question of why we would actually carry out fire and gas mapping in the first place. And we'll specifically get down onto flame mapping later in the webinar. So, number one, what detectors will respond to the hazard in question? Well, this is something that's answered during the fire and gas mapping process. We have to make sure that we apply the correct technologies to detect the anticipated fire hazard. Where should the detectors be positioned? Well, we have to make sure that we place our detectors in the most optimal location. This can apply both to practicalities of mounting as well as coverage, the actual coverage percentage. Remember, we obviously need people to go out and maintain these detectors and to go out and look after them. So we need to make sure these technicians have easy access to the devices as they carry out the PMRs. How many detectors do we need? Well, in a time of cost restraints and budget coming under tight scrutiny, we have to make sure that we're not over-engineering our systems and that we optimise the number of detectors as far as possible so that our facilities can remain competitive. How can I be sure that the area of concern is protected to an acceptable level? Well, that's really quite crucial in the fire modelling stage of the fire and gas mapping process. At the end of the day, these are safety systems. We have to ensure that an adequate level of safety is achieved when we apply them. This issue of adequate coverage is a direct function of the performance targets which we have to set at the start of every project. And these targets determine the number of detectors we'll ultimately require, but we'll revisit this later in the webinar. In relation to these factors, this webinar is going to show how flame mapping actively contributes to project certainty by looking at how a designer would demonstrate optimised coverage, how they would reduce the time of design compared to the traditional methods, and ultimately we'll move towards producing a detailed design which meets the project objectives with respect to flame detection and also keep project costs competitive with respect to the number of devices that we actually require. So what is fire and gas mapping? Well, fire and gas mapping, it's a bit of a misconception that fire and gas mapping is simply the output of a piece of software. There's two primary factors in what's commonly referred to as fire and gas mapping. One, the engineering knowledge, which is fundamental in the design. And the second part is the modelling. Each of these factors in fire and gas mapping is crucial. And an adequate design rarely applies only one of these two phases. With engineering knowledge, the engineer has to identify the hazards of concern such that the escalation potential can be determined. Ultimately, we're limiting the extent to which a fire can grow and cause further damage. So this risk analysis, ultimate performance definition is crucial to an optimised as well as a safe design. The engineer also has to review any mitigation actions which are required or already in place to make sure that the inputs to the modelling are accurate and that the overall system will actually operate as we want it to operate. The engineer must also review the detector contributions in order to decide which detectors perform better than others or more effectively. This is not simply from a percentage coverage standpoint though. The engineer has to be able to determine if a detector, if it has a low percentage, is actually reviewing a particularly highly hazardous piece of process. And equally, a detector may have a high percentage coverage, but actually is monitoring a low or negligible hazard area. This detector would probably be able to be optimized. So the interpretation of the results of this modelling phase is absolutely critical in an adequate design. Equally important is that modelling phase, that second phase. Within the modelling tool, we have to make sure that we apply the risk-based requirements determined by the engineer without too much scope for error. Detector voting has to be adequately represented as well against what we're trying to detect. Obviously, this is very different with flame detectors, gas detectors. For example, you would set a gas detector to alarm at a certain concentration of gas, but you would set a flame detector to detect a certain size of fire. A flame detector will either detect a fire or it won't. So obviously the fire size does impact how many detectors you require, but this is a function of the risk analysis, not the detector set, so to speak. So this is a very basic point, but it is certainly worth noting that not all modelling tools contain this fundamental coding of detector operation. The modelling outputs of detector contributions and coverage are obviously also crucial and have to be referred back in the loop to the engineering knowledge to try and determine if our system is adequate. So looking specifically at flame detection, we first have to appreciate that what we intend to achieve with our detection devices is mitigation. Flame detectors themselves are safety barriers and trying to reduce the escalation of an ignition incident. So regardless of which risk assessment method is applied, of which there are obviously many different methodologies, flame detection will fall into the category of a safety barrier. The intention of this safety barrier, as we can see from the bow tie, is to limit the severity of an ignition and the growth of that fire. We typically expect flame detectors to operate at the second point in, around about fire escalation. Flame detectors are not typically designed to be able to detect the ignition or the incipient stage of a flame, so we actually have to wait until the flame becomes a visible or a flickering flame to allow our flame detectors to actually detect that source. We wouldn't want the fire to continue undetected into the large uncontrollable fire stage and certainly into the secondary fire stage. So we want to implement our flame detectors to be able to detect small fires to prevent them from becoming much larger fires. So I mentioned earlier on performance targets. Essentially, to summarize what a performance target looks like, it's a formal statement of what fire our detection system should be able to detect, or what we would want it to be able to detect. If we were to design a performance-based system, which is suitable for the hazards in question, we have to set this target fire size to push us towards not only precise coverage, but also the equipment which is going to pose us the greatest hazard. We don't have guidance like that in NFPA 72 or BASE 5839 to design the flame detectors against, as we're typically looking in unpredictable environments, especially if they're external hazards. So this inevitably leads us to performance-based design. The notion of performance targets is summed up by deciding if you would want the same level of detection in an area where the hazard is a high-pressure gas jet fire from a compressor, for example, compared to a diesel storage area with a finite diesel pool fire as the credible hazard. It's obvious that we don't want the same level of detection in these areas. Therefore, we can apply a risk-based approach to determine a target fire size specific to that area, which would become difficult or impossible to control. This would essentially then become our performance target with respect to detection for that area or that piece of process. An important side note to this slide here is that flame detection is that mitigation safety barrier. We therefore don't want to model what type of fire could occur in the area, as this is our flame detection target fire size. If the intention is to prevent the type of fire which could occur from actually occurring, then we should be setting our target at a smaller fire with respect to the radiant heat output. If we set our performance target at the size of fire that a gas compressor could result in if it's ruptured and ignited, then we can't credibly detect any fire prior to this stage. Therefore, with a system like that, little or no mitigation is actually provided by the flame detection system. So an example we see here is where the designer can specify the distance from the equipment that the graded volume would extend to, sort of inner and outer distance area there. And that looks quite like a hazard area classification drawing. We want to be able to specify what kind of fire size will occur within a given distance from a piece of equipment, and start to cause some potential risk of escalation. In this example, we can see a high risk, medium risk, and risk, which the designer can choose from. But this is very editable, and it depends on the methodology which is selected at the start of the project. We also have a special risk grade here, which is quite common, and that's really for areas where none of the standard grades are actually suitable for the hazard. We often refer to this grade as the get fail free card, as the designer gets to choose what size of fire they want to detect to and what the resulting control action should be. So, how do these performance targets actually play into our flame detection mapping? Well, crucially, flame detectors operate based on the inverse square law. The inverse square law, to put it simply, essentially means that when fire is small, the flame detector has to be much closer to that fire source to detect the resulting alarm, whereas larger fires can be much further away and achieve the same response. And these distances are calculated using the inverse square law to determine how far a specific fire size can be from a detector to give the alarm response. If we take the standard N-heptane pan fire, for example, which is approximately 40 kilowatts in radiant heat output, if a detector can detect at 30 meters, and we reduce the distance of the detector to the fire to 15 meters, the smallest fire that detector will be able to detect is a 10 kilowatt fire. So we've halved the distance between the detector and the fire, but the smallest fire it will be able to detect is actually a quarter of the size rather than half. And this is the inverse square law in action. This method works reliably up to fires of about 500 kilowatts in radiant heat output or greater. We start to lose accuracy at that point with sensor saturation and some various other environmental factors. But typically you wouldn't want to target fires larger than that anyway in the design, as you lose your ability to mitigate effectively above that range, going back to the safety barrier analysis earlier. It's also a lesser known issue that detector technologies actually struggle to detect very large fires, as the infrared sensors can become saturated by the flame stimuli, ultimately blinding the detector. But to be honest, that could cover an entire webinar in itself, so we're just going to concentrate on the flame mapping for now. It's pretty important to make sure that our flame detection mapping software can analyze the flame detection coverage using the inverse square law, essentially automatically. There's a lot of scope for error when you have to manually implement these kind of factors, so far more reliable is if you can just specify your target fire as you want to detect, and then start placing your detectors and analyze the capability of the devices to detect those fires throughout the entire area. We have a number of videos on the slide here, which hopefully won't be too laggy. Everyone should be able to see them. They do relate somewhat to the inverse square law with respect to the capabilities of flame detection devices. They focus in on desensitization of flame detectors in process environments or external environments. And essentially we need to be able to think like the detector that we're placing in the area. It's a highly misunderstood area of design, and desensitization is often overlooked, but it can have serious consequences on site if we don't account for this accurately. Often engineers will review the device data sheet and assume that the detection distance listed there to the square pan fire is gospel. Now, this is rarely the case, regardless of the technology. A lot of those tests are under lab conditions, and then we place the detector out into an external environment, for example, and the results can change quite drastically. The first video that we see on the left-hand side here, on the left-hand side, we have an infrared-based detector, and what the video here is going to show is a test chamber in our test container here in Aberdeen. You can see the little green LED. It's very, very faint, but when the video starts playing, hopefully it'll become clearer. And that detector is sitting completely healthy. It cannot see a fire. The detector on the right-hand side has gone into alarm. That's a visual-based detector. So there's a little red LED on that detector. When the camera pans round to the right, you'll see that there's clearly a fire burning at the end of the test chamber. But the test chamber is filled with a mist, a water mist. And what that simulates is a foggy environment or a wet environment where some mist in the background or within that external environment, common of, for example, offshore or any facilities near the coast where there could be some fog. So the detector light is perfectly healthy, detector right and alarm. We see with our eyes that there's clear fire burning there, but the infrared-based detector cannot see that flame. The reason the detector can't see the flame is because that water mist is absorbing the infrared radiation before it can reach the device. The detector light, being a low-based flame detector, can see through that water mist. There is still a degree of attenuation there, and there is still a degree of blinding, but as you can see, it's not nearly as severe as the infrared spectrum. So we would certainly expect the detector on the left to be able to detect that flame at that distance, but the water is absorbing that radiation from the fire. With the point of view of device reliability, you can start to see, well, the device is very reliable from a hardware standpoint, but we have to be able to map the capabilities of these devices in the real world to get true appreciation of how reliable the device actually is.
Hey, James, as you're giving that explanation, not to interrupt your presentation, but it seems as though it does get a little laggy when the video plays and when you speak. So it's a little unclear as your explanation as the video plays, just so that you know.
Sure, no problem. I'll slow it down, particularly for the video on the right. That could be a little bit of a problem, but I'll play the video a few times, and hopefully everyone can pick up what we're looking at. The video in the middle here is really just to let you see what a lot of standard flame detectors are actually seeing within the field of view. So on the right-hand side of this video, there's a steady state radiator. That's just emitting background radiation like a heater in your house. A steady state radiator, quite warm within the field of view. In the middle of the picture, there's a fire which has been lit, a square foot octane pan fire. We can all recognise that the flicker of it looks very much like a flame. On the left-hand side, we have a heater, similar to the heater on the right-hand side, just a little bit smaller, and there's a wooden chopping board spinning in front of that detector with holes cut in it. And what that's doing is chopping and flickering the steady-state radiator. Now, from the point of view of through the thermal imaging camera, it could start to look like a flame. And that can have two potential consequences. That could either result in a false alarm, where a detector looks at that and believes that to be a flame. Because of the radiation and the flickering, it can start to look like a flame. The alternative is potential desensitization. Some technologies will monitor that. It will start to interfere with some of the filters, some of the sensors, and it will actively lock that source out, not to go into alarm. But what we could end up seeing is that it then wouldn't detect a real fire within field of view because the sensitivity had been reduced. So when we're placing these detectors and when we're mapping our flame detection system, we really have to start thinking like a flame detector. And the video on the right-hand side, so before I actually press play, I'll just explain our test setup here. We have, in the bottom right-hand corner, you'll see a flame being lit. We have a square foot pan fire again. That will appear in the bottom right-hand corner. In the top left-hand corner, there's a detector looking down at where that fire will be, and it's about 8 meters away. So that flame detector is looking down at the flame. And the little image you can see in the bottom left of the picture is just a camera looking at the flame detector, which is looking down at the fire. The reason we have that camera there is just to show the LED so that we can see exactly when that flame detector goes into alarm. The LED, you'll see it when it goes red. It'll be this area here. I'm not sure if the little pointer is appearing on your screen. So what we have next to the flame detector is that chopping board again and the heater. So that's mounted next to the device, next to the flame detector, and that's emitting radiation, and that radiation is being chopped. So the impact that's having is that it's desensitizing that flame detector, because the flame detector is aware of that flickering radiation. It's blocking that out as a first source, not to go into false alarm, but it's blinding the detector from the actual flame. So I'm just going to press play on the view here. It might be a little bit live, but once that flame gets at the bottom right-hand corner, you should be able to see that. Okay. So the flame detector, you can see green LED sitting healthy. So it's not detecting flame. It's only about 8 meters away from the flame detector. That detector is sitting perfectly healthy. Now, what the engineer is doing is switching off the heater, and if you LED, it will almost instantaneously come into alarm, and the LED is turned red. So that's quite significant finding with respect to background. As soon as that background radiator was switched off, the flame detector, the desensitizing effect of that disappeared, and the flame detector almost immediately went into alarm. So that's not to say that we do not use these detector technologies, but we have to be able to account for it in our mapping to make sure that our flame detection mapping is as accurate as possible. One, for the environment that we're mapping in, and two, that the specific technology that we're using is mapped accurately. Okay. Another crucial element in the accuracy of flame detection mapping is accounting for the detector footprint correctly. Each and every flame detection technology, whether it's ultraviolet, visual, or infrared based, has a unique detection footprint. These footprints also vary between manufacturers and models of devices, even in the same technology kit. The detector footprints can be found in the detector manuals, but it's essentially easier to make sure that the modelling tool accurately reflects the precise make and model of the device being used. So the coverage analysis that way can be as accurate as possible and tailored to the device that's being implemented. Verifying the detectors against the standard M3260 test is also useful. These tests analyse each detector against the common false alarm sources and desensitizing aspects of an environment. These values are essentially used, again, to increase that accuracy of our mapping. There may be an occasion where the specific device hasn't yet been selected, though. So in occasions like that, you would typically want to apply a conservative generic footprint, which can then be remodeled at a later date to revalidate those initial design assumptions. So this here is really just showing the typical process of a basic flame mapping model. The first phase would be to import the 3D model of the facility to ensure that the modelling provides as accurate as possible a representation of the environment being analysed. In this case, we're going in the test ground here at Micropack. We'd then specify our methodology and add our target fire size grades. And this would be based on whatever methodology is selected at the start of the process. The designer then has to add in the existing or preliminary flame detectors into the model, making sure that desensitization and the specific flame detector footprint is accounted for. And this then puts us in the position to run an assessment, generating the coverage maps, which the engineer can then use to determine if the design is adequate or otherwise. If we look at a basic example here of an offshore module, Now represent two different methodologies with respect to flame mapping and the difference in detection design which can be possible. The first example we're going to look at is a geographic volumetric style assessment. In this example, a moderate risk grade has been applied throughout the volume, and this means that a target of 40 kilowatts radiant heat output has been specified throughout that volume. Again, this is the standard test fire which flame detectors are certified against. The voting configuration has been specified at 2 out of n as well. This method of grading is quite common in basic designs where the optimized volume solution is desired. However, as we'll see, this is a bit of a pitfall in design, and will also emphasize the importance of engineering analysis during the process, rather than solely relying on the software to generate layout for us. So when we review the coverage achieved, we can see that 7 devices are required to achieve what we termed as optimal coverage. The field of view of these devices can be seen on the image on the bottom left. As you can see, the software requires detectors to look at basic volumes to increase the percentage coverage, rather than specific equipment where the hazard may occur. The same target fire size has been applied throughout the volume, meaning that we're probably looking at a poor engineering design in this instance. To note what our coverage percentages represent at the top of the slide, green represents control action, or 2 out of n coverage, to the targeted fire size. Orange represents 1 out of n coverage, or alarm only, again to the specified target fire. Brown represents 1 out of n detection, so alarm only, but only when the fire goes to an unacceptable size. And the red represents any blind spots where there's no detection at all. So looking at a coverage percentage of greater than 70% for control action, we'd be happy from a safety perspective that the area is adequate, but this doesn't show us any form of optimized coverage. Looking at the percentage also, the 70% coverage, it doesn't really even tell us that the safety is adequate. So 70% is a good target, but 30% of the area may be completely uncovered. So even looking for that target 70%, we could assume that the coverage is okay, but again, the engineer would have to go and look into that. It's credible that an area with 90% coverage is actually less safe than an area with 70% coverage. If the 10% blind spot, for example, first scenario, is at the highest risk area, then that can't be termed as safe. Equally, if the blind spots in an area with 70% coverage are evenly distributed throughout the area, adding further detection would probably provide very little coverage increase against the cost of adding those detectors. Then the 70% covered area could probably be deemed adequate. Tying in with this, there is also a little bit of a warning here against using the software to generate that layout of detectors on its own to achieve a nominal target percentage with the fewest number of detectors. This is because we may start to converge at, say, 75% coverage, and adding many more detectors will only give a few extra percent. An engineer would determine the coverage is fine at 75 and move on with the truly optimized layout, whereas the software would have to keep going until it hit that 80% target. So we can look now at a more performance-based approach, which will use a risk assessment and grade each individual piece of equipment based on the escalation potential of a fire within its vicinity. Example target fire sizes can be seen here with the equivalent graded volumes, including a high, medium, and a low risk as red, orange, and green respectively. We also have the special grade color of blue, which we mentioned earlier on. So this method allows us to eliminate wasted detector coverage of areas of very little risk or no risk, target our detectors to the areas of concern to detect the fire sizes of concern. So we can see from the assessment that to achieve a comparable coverage of over 70% control action for all grades, we only require 4 detectors in this case. Coverage of each detector can be recorded and logged and audited at a later date with full device location justifications provided for each individual piece of process equipment. We also have the breakdown of coverage percentage listed for each individual grade, which the engineer can interpret and determine if adequacy has been achieved or not. In this particular assessment, we also have yellow coverage in addition to the green, orange, brown and red from before. This represents the areas where the fast response alarm target fire size will not be detected, as no detector is close enough to the source to detect a very small fire, but as that fire grows and reaches the target fire size for control action and shutdown, two-out event detection will be achieved and the system would achieve that voted control action coverage. This can be summarised as achieving no fast response alarm, but suitable control action. So that's generally regarded as acceptable coverage, the percentages that fall within that yellow bracket. When we analyse the coverage in either case, it's important to analyse the area as a three-dimensional volume. We therefore want to review the coverage at varying elevations to assess the adequacy of that layout. This is something, again, that the software can't really analyse. So in this case, we have elevation slices at 1, 3, and 4.4 metres of the local deck. And the engineer can have a look at what the anticipated risk is, the anticipated hazard, and then determine what elevation is of the greatest concern and look at the coverage at that specific slice. Another tool that we can use to determine if we can optimize layout is the Detector Contributions table. This table allows us to check the coverage of each individual detector in the area. The first column next to the detector tag under individual shows the percentage coverage that individual detectors provide within that graded volume. That changes slightly when we look under the 1 out of n, 2 out of n, and greater than 2 out of n coverage columns. What's represented there is what would happen to the overall coverage if that specific detector is removed from service for whatever reason. So for example, if FD002 is taken out of service, our 1 out of n coverage will reduce from 95.5% to 85.5%, and so on and so forth. When we review that detector adequacy, you can see that FD002 is the best performer with respect to individual coverage at 68%. It is important to note that this needs further review. When we look at FD004, we can see that it's the second best performer with 48% individual coverage of the volume, so we're sitting second in the table there. But when we look at the reduction of 2 out of n coverage when this device is removed, we see that it's actually the weakest detector when it comes to providing executive action coverage. It takes the overall 2 out of n coverage of 76.5 down to 58.9, the lowest reduction of the 4 detectors. It's for this reason that it's crucial to make sure an engineer determines what's adequate or otherwise. If we rely on the software alone to lay those detectors out, the tool will inherently weigh towards one of these factors which could provide misleading results. The engineer must decide within the context of the area which voting arrangement of graded volume the design should be weighted towards. So finally, coming back to the issue of overall system reliability. With respect to flame detection, there are 2 different areas which require analysis. Design reliability should be analysed in light of what type and size of fire we want to detect, and through mapping out a system which, within the bounds of engineering judgment, will work whenever there's a demand. This will help to optimise the system and will provide justification of any device placed within the project. Basing this process on a risk-based method allows us greater scope to optimise the system and can increase the safety of the system by focusing in on those higher risk areas. We then clearly have to review the device reliability, accounting for hardware and software reliability, the response time of the device, the suitability of the technology as a flame detector, and the reliability of any potential mitigating functions. So, summarising the importance of each of these factors, we can picture two scenarios. One where a great deal of time, effort and money is spent on fire and gas mapping and purchasing the optimised number of detectors to ensure an adequate level of coverage is provided. The problem in this scenario is that none of the devices are certified as having reliable hardware, and the cheapest option was selected. This would result in a high probability of hardware failure on demand. So in the event of a fire, would we really want to rely on that system, the overall system? The second scenario has a project buying only the most reliable hardware with rigorous certification processes to ensure that hardware reliability of cell 3 is achieved, to give an extreme example for fire and gas. The problem with this scenario is no coverage analysis had been carried out, and there are too few devices installed to cover the areas of the highest hazard. An example I've seen many times is a flame detector pointing at the ceiling, for example. Would we really want to rely on that system to be reliable? It's therefore important that we deal with both sides of this coin. If we want to ensure that a reliable design coverage using reliable certified equipment is applied, then we may be able to actually term our overall system as being reliable. So thank you all for your attention. I appreciate everyone dialing in to the webinar today. And I'll hand back over to Ted to run a quick Q&A if we've got some time.
My apologies, James. Thanks so much. I was on mute. So James, if you don't mind, I'll go ahead and I'll have you answer the first three questions here, and we'll go through the time. And if we run out of any time, we will get to the other questions. We are going to write them all up and give a written explanation to every single question that was asked here. But the first one, James, if you don't mind, is the first question is what type of 3D model import? So I believe maybe what type of file can you use to import into this data? Do you have an answer to that one?
Yeah, certainly. The 3D models that can be brought in, there's a huge number of different model formats that can be brought directly in. STL, .obj, DGN, FBX, .3ds. A lot of essentially, if a model is open source, then we can certainly bring it into the software, and there are a number of other models that can be brought in as well. Generally, if it's a proprietary model format which can't be directly brought into map, the software that we use, you would typically be able to do a single conversion from the software you use to build the 3D models. So there's quite a lot of flexibility there to be able to bring the model in.
Fantastic, thank you. The next question here for you, and if any of these questions, James, would be better answered in a written response or maybe shown with pictures, by all means, we can just refer to the document that we're going to create together. But this next question is, have you ever done any work on coverage performances for heat detectors, either spot type like API 14C, fusible plugs, pilot sprinklers for NFPA 15 deluge systems, or linear heat detection?
That's a great question. For the applications where those types of technology that would be used, we generally have good prescriptive guidance where there's not generally a great deal of modeling required, unless it's a very bespoke design area. If you're designing like the Burj Khalifa, I suppose, then you would need to do some performance-based analysis there. But in oil and gas, whenever we need to use a heat detector, it's typically an enclosed area, and we generally revert back to, as I say, NFPA 72 or an appropriate guide like that. If it's an external area, generally we want to move away from that type of technology. We've got a lot of history, a lot of experience, and a lot of data that shows that those types of detectors are simply ineffective in a process area. And that actually goes to modelling as well. If we were to do some heat detection mapping, for example, it's so unreliable because we have no idea what the environment will be on a specific day. And we also find that even a slight breeze or a slight wind will take a lot of the hot products of combustion away from heat detectors in an external environment. So it really depends on the environment, I would say, for that query.
Fantastic. Thank you so much. Let's see here. Next question. What typically causes saturation of the detector?
Yeah, good question. So if we think about what a flame detector is actually looking for, it's generally looking for the flicker of a flame at a specific pattern that will give us that alarm signal. If you think about a flame detector at a point of ignition, and let's say it generates a 10-meter gas jet fire with a hugely intense radiant heat output, if your detector is very close to that type of fire, then the flame detector really can't get a recognizable flicker because it's too intense, and the sensors essentially just become saturated. And if we look at a triple IR detector, for example, where it's looked for a ratio change across 3 different sensors, there's really very little ratio change because all 3 filters just register intense radiation. And that has the impact a lot of the time of simply blinding the detector when those sensors become saturated.
Excellent. Thank you. All right. They keep coming in. Let's see here. See how many we can get to today. So I have another question that I will answer. The question is... All right. So it says, based on your example, it looks like the certification document covers the overall model number, series of the device. Do manufacturers also provide certification documents based upon individual serial numbers of the device? So each device has its own certificate. That's a great question. And to answer that one, certification is based around, or at least most certifications are type certifications. So they can even be a family of products. And so the analysis is done based off of, let's call it a worst case. So the device that is, I don't want to call it poorly designed, but the one that has more risk involved, that's the one that's analyzed. And then the others that are have less failures can be grouped into that certificate. So if you have a family of, say, 4 or 5 different types, but they're all basically similar, you can do a family certificate. So more than likely, they are not based around the serial number of our product. They're based around that model number. As long as they're all built the same manufacturer, go through the same procedures. So you do not need to have a certificate for every product. But that's a good question. I don't think I've ever been asked that question. All right, next question here. What would exida recommend if a CIF meets architecture constraint and PFD average, but fails systematic capability, and clients don't want to use a different device? That's a tricky one, right? Because we all know that your cell capability is only as high as your weakest link. And if you're saying that your systematic capability from that manufacturer is lower than, let's say, the architecture constraint, so that PFD average, personally, exida would say we don't recommend using that product that has that that lower piece of it. However, do know that an end user can do anything that they want, right? So they just have to provide that justification. They now become liable, and they have to just show why they use it in a higher cell rated system, but they need to provide that justification. There is a clause in 61508 that talks about like an N+1, right? A variable +1 for systematic capability. I think it's in I believe it's like clause 7 of the second part of 61.508, where it actually will talk about like an N+1 for systematic capability. And personally, I don't recommend people trying to stretch it, because you can use proven in use. You can show, hey, look, even though this manufacturer doesn't have the best quality management system, we still feel it's great because we've used it for 15 years. We've only had a few different failures. So you can provide your own justification, but just know that there's a reason why that manufacturer didn't meet that level of capability, and you just have to provide your own liability and risk to that. Okay, I am at 11 o'clock, or excuse me, my time's 11 o'clock. We are going to take the rest of the questions. There's a bunch of grouping of questions on how to use fire and gas systems correctly. Can you take SIL credit in a type of SIF? Because a lot of people, they discuss about mitigation, and I will go ahead. I'll get all those questions answered for you. I'll write them up to you. Each person on this webinar will get a copy of this sheet with the full explanations. And I don't think and one other thing I do want to clear up is there was one question that I tried to answer on the fly that I don't feel I did it justice, but just know that the question was in regards to getting a product certified to different standards, and older standards and newer standards. And basically know that when a product's first originally certified, it goes through the RICR, it goes through all the requirements of the standard. And if a new standard comes out, if that product hasn't changed, it's been completely the same, that certificate's never been withdrawn, it's never lapsed in time, that product is considered certified, it's completely fine, and it's confident for use in that safe system. Just because a newer standard comes out does not mean that it now becomes invalid. So I just wanted to clarify that. I don't think I answered it on the fly like I wanted to, but so that does answer that question. Also, one more thing before we get out of here, we do have courses coming up. Please take a look. We have some fire and gas classes in Houston coming up, and some other functional safety classes as well. And by all means, if you want more information, we're constantly updating new white papers and new free information. We blast our social media just so you guys can get the latest and greatest. So join those sites. We really appreciate it. We'll be doing this again in about 6 hours or so. Or no, sooner, 4 hours. So thanks again for everyone's time. James McNay, I want to thank you so much for coming on today's webinar. I've learned a lot, and I even knew the presentation. So thanks again, and everyone and everyone have a great day, and take care for now. Thanks again, James.
Perfect. Thanks, guys.